Okay, guys. Today we'll be finishing chapter 12. I hope we'll finish most of it, or if it's not, then will be Thursday. Okay, guys. We stopped on the fact that the phenols is a weak acids. This is acting as a weak acid, and the weak acid with the base, this is a base here, strong base. It's a base, but because of the fact that it has strong base, so I give you salt plus. So this is a typical acid-base reaction when it comes to the phenols. Phenols is a weak acids. They will react with the strong bases or weak bases to make a salt and H2O. The alcohol is acting as such, but to less extent, because stability of the alkyl group here, the R, affecting this type of acid-base reaction. So alcohol is the same thing. You have acting as a weak base, and then a weak acid, and then you have a strong base here, and you have a salt plus H2O. This is a typical acid-base reaction, or sometimes called neutralization. So either or, meaning the same thing. Okay, guys? So, any question about this? So alcohols is acting as a weak acids, and phenols are weak acids, but the stability of the phenols more stable. So compared with the normal alcohol, phenols are most stable. Most stable. What's that?
You said that in a reaction, the alcohol will always be the weak acid?
Yes, the alcohol in this type of reaction in general, phenols are weak acids. Let me show you here. Just let me take this one out. Any question you have? Any question? So let me take this one here. Show you something here. If I have a phenol and the phenols are dissociating, correct, in H2O. So you will see that this one here, an acid is a compound that can donate its protons. So it will give the proton to H2O, and then this is double arrows, an equilibrium. Hydronium ion will be produced. It's a weak acid, and the phenolate, O, and then negative. So this is called phenolate. Phenolate is an anion. And the cation this is a cation called hydronium ion. So this is typical of what? A base? No, that's a typical of dissociation of an acid, weak acid, correct? Because it has double arrow. So the phenols donates its proton here. Its proton donates its proton to the H2O. The H2O will take the proton. You have 3 hydrogen, 1 oxygen, producing what? Producing hydronium ion. So this is acid, this is base, this is now a conjugate acid, and this is a conjugate base, if you can recall from the 1151. So that's an acid because it donates its protons here, and then the phenolate just without the proton, negative, called phenolate anion, and the cation is hydronium ion. Okay, guys, any question in the back? If you have a question, just raise your hand. please. So, I'm taking this one out, going for the next one. Here is the same, let's just show you the mechanism, what's happening. As I said, the mechanism is, you don't have to memorize mechanism. Now we showed, what I showed you is that phenols and alcohol can act as an acid. However, sometimes the alcohols and phenols can act as a base. So now, here it is. We said phenols and alcohols, they were acting as a weak acid, correct? Weak acids. However, in some instances, they can accept the protons, so acting as phenols and alcohols can act as weak bases. This acids here, bases. So they can accept the protons here. The protons will come here to make what? This is hydronium ion. Remember the H was R was hydronium ion, correct? This is hydronium ion because the H is R, but because you have R will be alkyl hydronium ion, alkyl hydronium ion. Now, this is really not the case of alcohol can because the small R is alkyl, but if you have a phenyl group, you have a phenols. Phenols always prefers to be what? To be an acid, weak acid. They can act as a weak basis as well. So what we call compounds that can act both a weak acid and a weak base, depending on what the conditions is, or what conditions are. So what we call this? Somebody will tell me? Somebody remembers? We call this one here amphoteric. Amphoteric compounds, meaning acids and bases. Both of them are weak, of course. They can act weak acid, what? Depending on the condition. Depending on condition, they are on conditions, chemical conditions. Chemical conditions such as temperature, usage of catalyst, correct? Adding of acid to them or adding as a base to them. So this is the way it is. But as I said, take it from here, the stability of the phenols are always prefers to be the phenols as a weak acid because it can act, if you put a very strong acid to it, it can act as a base, and you get then alkyl hydronium ion, correct? So if I have strong base here, for example, here it is, that's a phenol, and then you have a strong base, such nitric acid, then you can have an acid-base type of reaction, correct? So you can see that the acid will act itself. Here you have hydronium ion, something looking like this. HO, then you have the H's here, H here, and then nitrate. So phenyl, correct? Phenyl hydronium ion, or phenyl, because that's a phenyl, correct? Here it is. H. We have alkyl, phenyl hydronium nitrate, phenyl hydronium nitrate. So it's the same thing. You have the R can be H, that's a hydronium, but the R can be replaced by the phenyl group here, and you have the OHs all over the places, and then nitrate. Phenyl, hydronium, nitrate. Okay, guys, those are amphoteric acid, but if you look into the literature, you'll see that alcohol can act like this because the alkyl group is small, but the phenyl group is this large benzene ring, so they prefer to be in a weak acid. They prefer to donate their protons. Okay, guys, so here is what the chemical reaction, the most important chemical reaction of alcohols. This is excluding the phenols. Phenols cannot do this. Okay. The dehydration of phenols, it's very difficult. You cannot, the phenols, here it is, you cannot take this hydrogen and you tell me that there will be something like this here, correct, plus H2O, and then something looking like this one here, a double bond here, and maybe double bond here. So that's, so phenols will not go dehydration. However, alcohol, yes, that's always the advantage of alcohol. They have R, small r, CH2OH. That's a primary alcohol. Then you can have R, CH, R, H, that's secondary, 2 R's, secondary alcohol. Then R, CR, R, OH, that's a tertiary alcohol. That's a tertiary, secondary, that's a primary alcohol. Now R in the sense is small, so they can go dehydration. Phenols cannot go dehydration. No reaction here. No reaction, no hydration. Hydration means you are pulling hydrogen to make out of this hydrogen H2O then later on, correct? H2O out of this. So let's look at the dehydration of alcohols. Again, alcohols, because of the R small molecule, not a phenyl group, not a benzene ring, it is easy to dehydrate, means pulling out hydrogen out of this. Hydrogen plus OH means pulling H2O out. Dehydration means pulling out H2O out of the molecule, making what? A double bond. Making a double bond, meaning what? You make out of this alkenes. So the dehydration of alcohols, not phenols. Phenols will never go this bad. It's just the stability of the benzene ring will not allow this to happen. The small r in the alcohol, whether it's primary, secondary, tertiary, that will allow this to happen. So let's look at, can I take this one out? I'm taking this one out. You see the dehydration of this. This is what ethanol is a primary, because carbon is at the first one. And the whole thing is R, for example. The whole thing is 1 R. So you have 1 R and connected to the OH, that's a primary alcohol. Now, if you look at this ethanol, I can just show you how to visualize this. This is ethanol, guys. So look at this. This is OH. This is H, 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 H. So what's happened is that dehydration in the presence of a catalyst, correct, and the acidic medium, you can pull this one here out. You can pull this one here out as H2O. When you pull this one out, then the carbon will be what? 3 bonded. So it has to be 4. Carbon has to be 4 bonded. So then you are producing what? You are producing, here it is, you are producing double bond. So you are producing, so instead of, because I pulled this one here, so this one here, take this one here out. Just put it the same way here. This is H, this is H, this is H, this is H, and the OH in the top, I took it out. So when you take this one out, then you have a double bond forming. Correct, guys? That's typical for alcohol. And phenols, that's not typical. You cannot dehydrate phenols in general, okay? So in general. So now this is just the mechanism. As I said, the mechanism is going in. Alcohol is acting as a base here, base. And we said, but alcohol and phenols, they are amphoteric. H2O is amphoteric compound. H2O can act as a weak acid, can act as a weak base, both ways. Depending on the condition, you put H2O in. Okay, so the H2O can act both ways. The same thing with alcohol and phenols, they can act as both ways, weak acid or weak base, depending on what condition. Now you put strong acid on them, they will act as a base. So you get a base out of this, although this is a conjugated acid, but that's what's happened. You are producing a sort of salt. If that's HCl, for example, then you are producing the alkyl hydronium chloride out of them. So, and then from there, the next step is to take this. The next step is to take the H2O out, and then cleavage the H2O, break out the H2O out of the molecule, and then the double bond will be forming. So here's the next step. The next step is, see here, as I said, you don't have to worry about the mechanism. That's in advanced organic chemistry 1. After principle 2, you will take those mechanisms. So I'm not putting emphasis on those mechanisms, guys. So, but that's what's happened. When you add an acid to the alcohol, you will make hydronium ion out of it. The alcohol acts as a weak base. You add strong acid to it, you make a carbocation. This is carbocation for tetrabutyl carbocation or cation. So this is a tetrabutyl because it looks like this. All those are methyl group 3, and here's 3 methyl group, and it's missing its. So this is tetrabutyl carbocation. Correct, carbocation. Some textbook they take the carbo out, they said cation, but I like to have some other textbook they add carbo because you specify this a carbon cation. So whether you will add so there is some textbook will add a carbo cation in between tetrabutyl. So and then when you have this here, see here, one hydrogen here. Okay, so one hydrogen will be taken out. Will be taken out as here. So then you have to have cleavage. Those are remaining as they are. So then you will have a cleavage. You have a double bond here. That's the mechanism. As I said, I'm not putting emphasis. I'm not asking you about those mechanisms. Those will come after 12. What? 12. When you finish 12, you will have to take organic 1 and organic 2. So organic 1 and 2, they have details mechanism about how to do those mechanisms. I'm not asking you this mechanism. Okay, guys? Be assured I'm not asking you because that's higher organic chemistry to know the mechanism of this. So, and this one here is just to show you this. If you have the same thing we said about this one from the alcohol, and then you take the alcohol within itself as a cleavage. You take H2O out here, okay, and then when you take this one here, you produce what? You will produce a double bond, correct? You produce. So dehydration of alcohol always results in alkenes. So alkenes, double bond, always. Dehydration means pulling out H2O out of the of alcohol. You are producing what? Alkenes. Now depending on this alkene, the stability will be what? Coming from where? From the alcohol. This is tertiary alcohol. Tertiary alcohol is most stable. The most stable. So I can expect this one here, the alkenes here, is most stable because it's coming from what? Most stable. Most stable alkenes. If I have secondary, it will be less stable. The primary is the least stable. So that will affect the stability of the alkenes itself you are producing. So this one is very stable because it's coming from where? Coming from tertiary. So the secondary is alcohol is less stable, and the primary alcohol, those are alcohols here. Those are alcohols. So there were results. The results is dehydration is alkenes, and the stability of alkenes will depend on the stability of your alcohol to begin with. So this one here, least, not less stable, least, ever least stable. So the primary alcohol, the least, ever least alcohol. So therefore, you can see the stability in the physical and chemical properties. The tertiary butyl alcohol, if I keep it inside the lab, it will start solidify, make out of it solidify, stable. The ethanol, if I have it in a lab, sealed, I mean, you can come after a couple months, most of the bottle are empty, most of the bottle is empty. It's evaporated. It's not stable. Any heat, any warm weather, anything inside the lab warming up, this ethanol will out. However, the tertiary butyl alcohol, you can come after 20 years, the same as is. So that's the stability affecting its boiling point, melting point. So that's what you mean by stability. So those they don't react as such as ethanol. Ethanol is stable. So, and it has least physical and chemical properties compared with the tertiary alcohol. So, again, this mechanism, I'm not going through that. As I said, this is organic chemistry, so don't worry about it. Nobody will ask you because that will be your task when you take organic chemistry 1 and organic chemistry 2. And you have a lot of mechanisms. You have SN1, SN2, you have elimination. All those are mechanisms. You have carbocations there. So now, if you have an alcohol, okay, so you have an alcohol, and this alcohol is what? What type of alcohol here? This one here. If you have type of this, how many? First, what type? What type of alcohol is this? Come on, guys, don't let me down. What type? Secondary? No. Tertiary. Correct. Why? This is the whole thing is R. The whole thing is R. The whole thing is R. 3 R's connected to the carbon that carries OH. That's tertiary. That's the most stable one. Now, because most stable one, we can expect to produce alkenes. But this time, because of the fact that they are there adjacent to OH, adjacent to 2 hydrogens, so we can expect to produce what? We can expect to produce, first of all, this one here. The second, we can produce this one here. So two possibilities to pull out the OHs, correct? So if we are pulling the OH from here, so the double bond will be where? So I'm pulling here, those here, correct? So I'm getting what? This one here. If I'm pulling the OHs from this side here, I'm expecting to have this. So this is plus here. Okay, guys? So there is a possibility sometimes if I have the OH attached to this is just typical tertiary alcohol. It's typical because very stable. Primary alcohol, you will not see that as such. You will not see that such. So tertiary alcohol, because stability is very high, and it can pull you have two chances. You can pull the hydrogen with this red circle, or you can go the other route is the blue circle. So in both ways, you can reduce here plus H2O, and here plus H2O. No, that's wrong. Here, so you can see that's much better. Plus H2O. Okay, guys. So you have two ways to pull out those H2O from adjacent from the adjacent carbon. So the OH that can take the H from the adjacent one left, or it can be taken the right, and on both sides you will see your double bond is changing. The double bond location will change. Okay, guys, so you are producing in both ways two alkenes. As I said, this typically seen by the most stable alcohol, the tertiary alcohol. Okay, so primary alcohol will I doubt it can do this. You'll get just one alkene out of it. Okay, guys, let's take further. We have this is until now dehydration. What's other type of reaction of alcohols? Well, the typical one beside dehydration, they can react with the acids, correct? And they can react and they can produce with the acid, as we have seen. When you add them to acid, they can make alkyl hydronium salt as acting as a base, correct? But sometimes what they do, you are pulling the H2O, and the X will come here. That's negative. Remember? So then the X here will come and take over the R. You get Rx plus H2O. So the H here okay, guys, so this is a possibility to dehydrate the alcohol, take the OH, the whole OH out, and that's only if you have what we say from the beginning. What we said, you have to have what? Strong acid. Weak acid will not do it. So if you have acetic acid, that will not reaction will not go. You have to have a strong acid to do this. Are you following me here? And you have to have stable alcohol, tertiary alcohol, or secondary alcohol. Primary alcohol most probably will not be able to do it. Are you following me here? Always the stability of alcohol is affecting type of reaction you have. Okay, so you add strong acid to it, you can pull out the OHs here with the Cl. I mean not the Cl, with the H here. Let me see here. You can pull out the OH with the H to produce H2O here. And then the Cl will come and attach itself to the tertiary butyl carbocation. Okay, so let's look at some of the reaction. Some of the reaction, it's not really a reaction. It's not. We did not say that this is a reaction, but this has to do with the stability and the explanation why is tertiary alcohol more stable than secondary alcohol than primary alcohol. It looks like the stability comes because of the hydrogen bonding. So if you have this carbocation and all this R, I'm just looking at this. This is tertiary, correct? Now, if you have whatever the compound is, now we'll have, oops, sorry. we'll have here the alcohol, tertiary alcohol coming out. Now, if I will put this one here even further, now you will see here this tertiary alcohol, it can have hydrogen bonding with itself, correct? And because of the stability of the carbocation, so I can have HO and then C R R R. Here we are. So now we have here, this is a hydrogen bond, and this is another hydrogen bond, two hydrogen bonds. So, and the very stable what? Carbocation. So this is hydrogen bond, that's the reason behind the stability. So the stability of those carbocations or the tertiary is they can make themselves hydrogen bond. So they make hydrogen bond. What's hydrogen bond? Hydrogen bond is the bonding between hydrogen. You have to have hydrogen for one side, plus you have to have oxygen or nitrogen or fluorine. So if you have combination of hydrogen with nitrogen or fluorine, thus you are producing HO, you are producing HN, you are producing HF, and this is called hydrogen bonds. Those are called what? That's not in the PowerPoint, but at least it's not explaining why this stability is coming from. Well, stability is the carbocation is huge in size, so therefore stability, and the stability is utilized by the hydrogen bond. Hydrogen bond is a combination of hydrogen with oxygen or with nitrogen or fluorine or with all those three atoms, correct? If you have them in a molecule. So in one molecule, one alcohol will deliver oxygen, the other one will deliver hydrogen. So we have two hydrogen bonds, correct? So this is not inside the PowerPoint, but at least you will cover this one here even further in more details in the organic 1 and the organic 2. It's very important. Stability of a molecule is always utilized by the formation of hydrogen bond. Now, as I said, I'm not going through the mechanism of this adding the strong acid to the alcohol. We went through that before, but the main thing is you are pulling OH out, and the chlorine will come to this. This will be, what this type of alcohol is this one here? Somebody will tell me? What type? Tertiary or secondary or primary? What type? Come on, guys, don't let me. That's a primary. See? Connected to the first carbon, and all the rest is R. So ROH. That's a primary alcohol. Least stable of all. Least stable. So in order to have this one here, to pull the H2O out of this, so you will have to have catalyst, you have to have a heat. So you see a lot of extreme conditions. But if you have a tertiary butyl alcohol, that will be easy, because stability of the carbocation is very high. So that's the least stable. So, but anyway, so you get this. We call it alkyl. That's this alkyl group here, R, alkyl and halide. Halides means can be chlorine, fluorine, bromine, iodide. So all those four, the halides, okay, for any one of those four. However, the fluorine will not be part of it because HF is really weak acid, so we'll not see a good results out of weak acid. You have to have strong acids, which are the HCl, the HBr, The HI, those are strong acid. This is weak acid. This is weak acid. HF is a weak. It is, write it down here. Is weak acid, so you can't expect. So this is HCl. HCl, very strong acid. A weak acid will not deliver this. Okay, guys, so this is a mechanism. I'm skipping this. Don't worry about it. The same thing. You produce a carbocation. This carbocation, then you'll have the hydronium-like alkyl hydronium cation, and then you will start the halide. The chloride will come in and attach itself, and you pull out H2O. So anyway, so we'll not go through the mechanism again. This is the preparation of alkyl halides. That's the mechanism, but as I said, don't worry about the mechanism. The main thing is ROH plus strong acid, can be HCl or HBr, Br, hydrobromic acid, hydrochloric acid, or hydroiodic acid, those three. And then they can pull out here H2O plus Rx. So Rx is the alkyl halides, and those halides are chlorine, bromine, iodide. The fluoride, it has to go a different mechanism because HF is a weak acid. You not get things you are expecting. Now, this is just the halides here. There is another route to produce the halides. That's what you say. This is one route here. The second route, you take this, the thiol here. This is thionyl chloride. This is sulfur. Sulfur means always an organic compound called thiol. Anytime you have not L but thiol here. Sulfur means thiol. Sulfur means thiol. And if it has SH here, SH, that will be thiol. Replacing like the OH alcohol, this is thiol. But by itself, here this is thiol without the L, correct? So you have a thionyl chloride, correct? And then we have to get this one here. The chloride will come and attack it. You get Rx, RCl plus SO2 gas plus then HCl gas. Okay, so that's type of reaction. And you need the heat. And here is another type of reaction. And as I said, they show you here, you can take the phosphorus trichloride, the phosphorus tribromide, the phosphorus even iodide will work. But the fluorine, because coming from weak acids, we are not expecting that to happen. So you have phosphorus trichloride or phosphorus tribromide or phosphorus triiodide will come and react with this alcohol, the primary alcohol, and then make Rx. That's how you produce the alkyl halides, and the phosphoric acid will be produced. Okay, guys? So the X can be chlorine, bromine. Same thing here with the reaction we say. They have to come up from strong acid. Chloride, bromide, iodide. The fluorine atom is not part of it because it makes hydrofluoric acid a weak acid. So, this is comparison between alcohol and phenols. As I said, phenols is very stable, very stubborn, does not undergo any type of reaction easily. And you can see, we said if we have the alcohol, remember we said alcohol, and then that's we added an acid to it, then we get the RCl, for example, plus the H2O. Here you can add phenol, correct? And you can expect to produce with HCl, guess what? You make a salt out of this. You cannot break the system. So what you'll make out of this, you'll make out of this hydronium ion, H here, and H here, correct? And here is the Cl minus, and here's plus. Okay, guys, that's what you can make. However, you cannot get H2O. You cannot pull H2O out of this. So you cannot get this one here, like this reaction here. Let me just show you this type of reaction here. This I showed you, that's direct, you produce this. But if, oops, sorry, if we try to get this one here, your answer, if you get multiple choice, so the reaction is no reaction, your answer is no reaction. If I have a phenol here, correct? So if I have a phenol here, for example, and I have OH, and then you add an acid to it, whatever. So you cannot produce something like this here. You cannot pull H2O out, correct? And make this one here is negative, and here's positive, here's negative. This cannot be. You pull OH out, correct? Here it is. So this is OH, and you are pulling the OH with the H. So, and then here is your byproduct is H plus H2O, correct? You are producing, you are taking this with those, correct? And then you have this type of reaction. That's not the case. Remember, that's will be phenolium ion. That's not existent. That's not existent. Okay, guys. But this one here is very, very hard to pull out those electrons. So what will happen is that can happen, but you cannot pull H2O out. So this one H2O cannot be pulled out, but you can make what? You can make out of it a salt. That's a reaction here. Okay, guys, that's a reaction. But to have something looking like, you are pulling H2O out, and then you have something looking like this, that will not happen. That will never happen. Okay, guys, so remember, phenols are very stubborn. They are not allowing their ring to be destroyed easily. The only thing you have to do some type of destruction of it, of the whole ring, and then make a combustion reaction, which is even phenol will not combust 100%. You get soot out of it. But anyway, this type of reaction, as you can see, this is not allowed. You cannot pull those here out and have this one type of reaction. However, you can add to that. You can add the OH HCl. You can produce something like this. That's allowable. That's allowable. So you can add this allowable, but you cannot pull the whole thing out of producing H2O out of it, and the phenol ring now is positive charge, and the chloride is there. It's not existent. Okay, guys. So yes.
We cannot dehydrate phenol.
What's that?
We cannot dehydrate phenol.
No, you cannot.
Okay.
You cannot. But if I have a cyclic ring, then yes, I can do that. So, for example, that's totally different. This is three double bonds, and they are not fixed in space. They are moving around. That's the reason I put this one. The circles here I put designating that those three double bonds are not fixed in space. They are moving around. So you put a circle on that. However, if I put the cyclohexanol, that's a doable. Yeah, that's not, the stability is not compared with the phenols. So if I have something looking like this, so cyclohexanol is OH, H, then you have H, this carbon has H, each carbon has 2 hydrogens, H, this carbon has 2 hydrogens, H, H, then H, 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 H. Can I, and this is called cyclo, 6 carbons, correct? Carbon 1, 2, 3, 4, 5, 6. Cyclohexanol, correct? Can make dehydration, yes or no? Yes, I can. I don't have this restriction of the double bond, triple bond. There's no single bond, no double bond there. Okay, so I can dehydrate, take this one out. What I'm getting out of this dehydration, I'm getting something looking like this. Double bond here. All those, the H's here, it's taken out. And then you have H's here. The H is taken out. Here's carbon, carbon, and then H's, H's, then H's, H's. So you are creating a double bond. You are making alkenes out of it. You are making what? A double bond. You are making a double bond. So H, and here OH's, here's H. So all those H's. So what we call this one here, instead of cyclohexanol, now you are making out of this is carbon 6, ENE, cyclohexene. And you don't have to number it because it will have always number 1. So always number 1. 2 over the double bond, and so on. So that's cyclohexene, yes. That's we can, even in the experiment in the lab, you might be able, I think there is something in your lab in organic 1 and advanced organic 2, you'll be able to do this dehydration of cyclic rings. That's easy. This can be done in the lab. I think we can design even experiments, temperatures, very mild temperatures, 120, 150 degrees. It's not water baths, for example. But the phenols is not. Phenols are very, very resisting to any changes. You cannot do that with phenols. Just the fact is the triple bond system, the ring, it's making it very difficult to react. Other chemical reaction, oxidation, well, the oxidation of alcohol, believe it or not, if you add too much of oxygen, pure oxygen, for example, alcohol, pure oxygen here, you make pure oxygen, you make CO2 plus H2O plus H2O plus heat. That is called combustion. Combustion means you can combust. Combustion reaction. This is a combustion reaction with pure oxygen. But we can use an oxidizing agent such as permanganate, potassium permanganate as oxidizing agent. We can use hydrogen peroxide. That's another, those two famous oxidizing agents we use in the lab. So you can, the alcohol, primary alcohol will give us, will be oxidized to aldehyde. So let me write this one here. Hold on, I'll take this one now out and just example for you here. Maybe I need, so guys, here it is. Primary alcohol will be oxidized, oxidation. Again, we will not use pure oxygen. That's a combustion reaction. We are using an oxidation using one of the oxidizing agents such as potassium permanganate or hydrogen peroxide. Those are very good oxidizing agent and strong oxidizing agent. Primary alcohol will give you the aldehyde. To what? To aldehyde. The aldehyde then will be further oxidized by those two here. Okay, to what? To carboxylic acid. To what? Carboxylic acid. I will give you an example of this. So if I have primary alcohols such as ethanol, correct? So this is ethanol here, HOH. This is H, this is OH. You oxidize it, you pull out H2O, then you produce an aldehyde called ethanol, CH3COH. Correct? Plus, you produce this one here, ethanol. This one ethanol. Oops, sorry. This one ethanol. This one goes to ethanol. It has a common name. As I said, we are not looking at common names here, but at least common name called acetaldehyde. Acetaldehyde or ethanol. Ethanol is IUPAC naming, that's the correct name, that's what we are always looking at. We are not looking at the name, the common names. Don't forget about common names. We are looking at the IUPAC name. This is IUPAC name. That's the recognized and honored. This one just a common name. So ethanol, the ethanol then come out here. This one here can be oxidized further, and then you get some out of this CH3, CO, and then you have OH. This is called ethanoic acid. Ethanoic acid, or common name called ethanoic acid, common name called acetic acid. Called what? Acetic acid. That's a common name. This is common. As I said, don't worry about common names. We are looking at the real IUPAC name. This is ethanol. So ethanol, OL, ethanol, AL, that's an aldehyde. Ethanoic acid, that's carboxylic acid, ethanoic acid. The common name, ethanol, the common name of ethanol called alcohol or wine. Commercial name is wine or beer. Beer and wine, they have mostly is water and then alcohol there. So alcohol is ethanol, that's the real name. The commercial name called wine or beer. The commercial name or the common name of the aldehyde coming out of oxidation by permanganate or hydrogen peroxide called ethanol, or a common name called acetaldehyde. You oxidize it further, you get carboxylic acid called ethanoic acid, or called the other name, common name is acetic acid. So that's a primary alcohol. So primary alcohol can go all the way to what? Through aldehyde to what? To carboxylic acid. However, the secondary alcohol here, so now we have secondary alcohol. Now the secondary alcohol, that's a problem here. You get ketone. So the first one here, the primary alcohol, it is primary alcohol. you get aldehyde, correct? Which can go further to what? Carboxylic acid. Carboxylic acid. Okay, guys, the secondary alcohol give you ketones. The tertiary alcohol, that's not in your what? Watch out. That's not inside your PowerPoint. I don't know why, but at least you have to be careful about this. So, using permanganate or hydrogen peroxide, this is no reaction. So, now we have three types of oxidation. Not combustion, pure oxidation. That's oxidation using oxidizing agents such as hydrogen peroxide or potassium permanganate. So the primary alcohol gives you aldehyde. Then it can be oxidized further to carboxylic acid. The secondary alcohol gives you ketones. Tertiary alcohol, no reaction. Please, right? Take a snapshot of this because you name it. You need it for the final exam. The final exam and the quiz and exam. But final exam, they bring something like this to see if the students are really recognizing the oxidation of an alcohol. Primary, secondary, tertiary. So the primary, we said aldehyde, and then it goes to carboxylic acid. The secondary alcohol, such as here, this is a secondary alcohol, guys. Okay, guys? So that's a secondary alcohol because you have two R's, and here is your OH. Okay, what's happened here, you make out of this one here, CH3, COO, CH3. That's a ketone. This is a ketone. The common name of this called what? Acetone. The common name is acetone. And the real name, the IBC name, this is secondary alcohol, correct? 1, 2, 3, propanol, 2-propanol. So this is 2-propanol. 2-propanol is secondary alcohol. 2-propanol gets you to 1, 2, 3, okay, acetone, or the acetone commercial name is what? We call it propanone. That's the IUPAC real name, propanone. You have O-N-E at the end, propanone. Propanone, that's the real name of acetone. Okay, so the other common name, here's a methyl group, here is a methyl group, and here is a ketone group, so dimethyl ketone. Dimethyl ketone, but we don't use this. Don't worry about it. But we say this is propanone, or a commercial name is acetone. So tertiary alcohol, there is no reaction. Tertiary alcohol is no reaction. So everybody has this. Please have this ready for the final exam. I'm sure they bring this one here in the final exam. So let me take this one here out, and let me take the okay, guys, that's what's the oxidizing agent. If you have a secondary, will give you just a repeat here. Secondary will give you a ketone. That's a secondary alcohol. Primary alcohol give you first an aldehyde. Aldehyde, you go carboxylic acid. This one gives a ketone. Tertiary alcohol, the answer is no reaction. So no reaction. So no reaction. Okay, guys? So going at this, let me look at what we have here. Again, if we have to go to a mechanism, we are not going this. Here, guys, what did I say to you? Anytime you have a cyclic ring, there will be always a reaction. Easy to pull out H2O. Are you following me here? So this is cyclohexanol, and you can make out of this cyclohexanone because this is a primary alcohol. Why? This time you are using oxidizing agent. Are you following me here? This is oxidizing agent. Oxidizing agent. You can use this one, or you can use permanganate, or you can use hydrogen peroxide. If you use those type of oxidizing agent, you get the ketones out of it, correct? Of the secondary, that's the secondary one. Why is secondary? The whole thing from here called R, and the rest from here called R. So this carbon is connecting itself to the OH, but it's connected to 2R of the rings, part of the left and part of the right, or above the OH and lower than the OH. So that's a ketone. Correct, guys? That's a ketone. Now, in the sense of you are not using oxidizing agent, you can produce what we said. You can produce something like this, plus H2O. You can pull those out together. What's the condition we have to use? Somebody will tell me? Come on, guys. Strong what? Strong acid. See the difference of condition give you different products. If I use oxidizing agents such as hydrogen peroxide, permanganate, chromium 3 oxide, those are oxidizing agents. Those will give me ketone because cyclohexanol is a secondary. They have to give me ketone. However, if I have strong acid, then I pull out the H2O by itself and making a double bond, make alkenes out of it. Correct, guys? Just to remember that, the difference between those two. Now, if you have here the alcohol, primary alcohol, you oxidize it, you get what? An aldehyde in between. And the aldehyde goes to what? To carboxylic acid, correct? And this is, you can look how many carbons you have, and then you can, this is octanol. This will be octanol, octanal. Aldehyde will be octanal, Al at the end. And then octanoic, octane. Take the E out, octanoic acid. Octanoic acid. So octanoic, let me, oops, it is. From octane, octanoic, take the E out, octanoic acid. So aldehyde, octanal, oic acid, that's the acid. Okay, guys, all, that's the alcohol. Okay, guys. Here you can, you see here, this is with the help of the PCC. The PCC is pyridinium salt here, pyridinium chromium, pyridinium chlorochromate. This is a catalyst used to stop this further to what? To the acid. So the acid will not go further. Why? Because you are using a compound that's prevent this further oxidation. So this one here prevents further oxidation. So if you use this type of compound, this compound will prevent the aldehyde going to carboxylic acid. So this is an aldehyde, and it will stop there. So this is an aldehyde, this is an alcohol, that's primary alcohol, goes to aldehyde and stops there. There here is not allowed. Why? You are using a compound that's prohibited this reaction to go through. Okay, so the aldehyde cannot go further to carboxylic acid. And this is just the same condition in the body, human body, that's here given to you. That's the liver is doing. Sometimes the liver has to do this. If there's too much alcohol inside the body, and this is an alcoholic person drinks a lot of alcohol, then what's happened, the liver has to produce, oxidizing this alcohol to aldehyde, correct? To acid aldehyde, and then further to to carboxylic acid. Those are still toxic. Then further to carbon dioxide and H2O. So the liver does that with the catalyst. The liver is utilizing an enzyme. Here it is, enzyme called, you don't have to memorize, just nicotine imide adenine dinucleotide. This is an enzyme produced inside the liver. As I said, did I mention that the liver is the manufacturer of enzyme and hormones? I think I did, correct? Did I? Yes. Liver is the manufacturer of 90% or more, I think, of all the hormones and enzymes. So if somebody has a malfunctioned kidney, that person can survive. But if somebody had malfunction in the liver because of the taking a lot of alcohol, that person will not survive. Because you need an organ inside the body that produces all your function, all your operation. Because the brain has control on it, it has order to do all this operation in your everyday life. And those are hormones and enzymes, correct? And failing those enzymes, then you'll see a lot of toxic chemicals, some of them here like carboxylic acid, aldehydes, ketones will be reduced without getting rid of them. So, and that's just an example inside the liver, what the reaction is, what this enzyme is doing. Okay, guys? So that's an extra information. Nobody will ask you. Bless you. So, this is cholesterol. Is cholesterol an alcohol? Yes or no? Yes. Cholesterol, OL at the end, correct? OL at the end, that's an alcohol. Now, is it primary or secondary or tertiary? What do you think? You tell me. Come on, guys, don't let me down. What's that? Tertiary? Come on, guys. You are letting me down. That's tertiary? No. What's the correct answer? Primary, correct. No, primary is not correct either. I tricked you. No, guys, don't let me down. This is carbon here, correct? And this is another hydrogen you don't see. So all the rest from here, this is R. All the rest from here, another R. So if I have carbon connect to OH and H here, this H is here, correct? And connect to R and R, this is what? What's that? Correct. You made my day. Everybody's following? I want to trick you, said primary, everybody said, no, that's not the primary one. Because a carbon that carries two R's, that's secondary. The the carbon that carries OH has only one R, that's a primary. That's secondary, two R's. I have two R's here. All the rest is R and the rest below the whole thing R. So two R's I have. So this is what? Secondary alcohol. So cholesterol is secondary alcohol. If that's coming in the exam, I don't think so. It's coming, but at least you will know this is huge molecule, is cholesterol, which it's bad effect on blocking the veins, blocking the blood from going through the pump through the heart and be distributed through the whole body. So now here is the polyhydroxy alcohols. Those are very important, and you tell me what's the usage of them, please. So this is an alcohol here. You might be, it's not clear here. I'll put the OHs. This is the OHs. I'll put them down. I like to put them down. They put them up. So H and H. Now this is primary, secondary, or tertiary. Come on, guys. What is this? That's what? Double what? Double primary, because all the rest is R. And this is OH. Correct? That's what? That's a primary. And on the other hand, I can visualize this. The whole thing R. And this is connected to this. So double what? It's a primary, but twice, multiplied by 2. This called ethylene glycol. It has a common name. So and it has a common. This is a common name, ethylene glycol. But its name here is ethane diol. Ethane, see 1,2 ethane diol. Correct. So this is. Ethylene glycol is used what? In antifreeze. In what? Antifreeze. This is 3 of them. This is 3 of them, but now those 3 here, that's called glycerin. Somebody will tell me where we use glycerin. I told you glycol. Ethylene glycol is used, that's your antifreeze. The whole antifreeze is ethylene glycol. So those are 3 ones here connected. 1, 2, 3. And each connected to OHs. So this is glycerin. Glycerin itself is harmless. It's used to what? To lubricate machines. Your keys are not working, just buy from Home Depot glycerin, put your key of the car or key of your house or anything you want to lubricate will help you to lubricate. An excellent, harmless, not toxic lubricating chemicals is called the what? The glycerin. Okay, guys? And the third one here called what here? You can see, sorbitol, that's 4 of them. Not 3, but 4. That's another solvent. But the glycerin here is harmless, but if you add nitric acid to it, you get sort of what? Somebody will tell me. That's what we call commercially dynamite, correct? So what we call this one here? Dynamite. So the commercial name dynamite is coming from the reaction here. Yeah, let me show you, and then I'll stop here, guys. I'll stop here. So we are producing what? We are producing glyceryl nitrate. This is highly explosive compound. An explosive. You can call it dynamite, you can call it the bombs, you can call it whatever. But this is highly explosive chemicals. You have to take care of it when you are treating it inside the lab. So you cannot take it with just normal, you can't treat it as a normal compound. You have to be careful. I'll stop here, guys. I'll see you in coming Thursday, okay?